Hi, about a week ago I saw this interesting article about acoustic levitation using basically setting up ultrasonic standing waves to hold small objects in free air. This was in the context of chemical reactions. I thought it was quite interesting. It's quite a cool video with it showing a water droplet reacting with sodium in free air. And I had a look around YouTube to see what else there was, and there were a few examples, but they all seem to be like universities, and they all seem to be using fairly specialist equipment, but I couldn't really figure out how much power was involved. So I thought, well, maybe it's practical to do this a bit cheaper. So I did the obvious thing and just have a look on eBay at ultrasonic transducers, and I came across a few that look like this. These are designed for ultrasonic cleaning tanks. They sort of go onto the bottom of the tank, sort of vibrate the water, produce cavitation and clean stuff. This was the most powerful one that I could find at a sensible price. This is a 70-watt one, 28 kilohertz operating frequency, which was just under 20 quid plus about 6 quid postage to the UK, so not particularly expensive. They're a fairly simple construction. Basically what you've got two discs of piezoelectric material. There's two sort of thin electrodes. This one connects to the centre of the two discs and this connects to the top one, and then there's a bolt that goes to the middle that also connects to the bottom one. So there's a block of steel on the bottom and aluminium on the top. I assume that the idea behind this is the steel has a higher mass, so that basically stands relatively still, and this vibrates against the inertia of the steel. I think obviously the shape of this is probably significant in terms of it probably does something similar to the function of a horn for an acoustic transducer. It came with this little stubby thread on the top. I think what they did, they just drilled through the whole thing, tapped it. The bolt from the bottom, there's a big Allen bolt that goes up through the steel part through the centre, screws into here. So I think the idea is that gets screwed in a little bit, then that then screws onto the bottom of the tank. This surface has got an interesting texture. It looks like some sort of bead blasted machine texture, so I'm not sure whether this would normally be bonded onto the tank or whether that's something to do with the acoustic properties. Yeah, maybe that is for a bond or something. It's obviously a very deliberately roughened surface. I've not really seen the tanks these go to, so I'm not really sure about that yet. They do also sell these with the driver boards, but I didn't buy the driver boards because I've looked at a few schematics of ultrasonic cleaners, and they tend to use unsmoothed mains so that the ultrasonic signal is going to be basically modulated by 100 Hz mains, which in the context of a cleaner is actually probably quite useful because it will give you some extra sort of rattling of whatever you're trying to clean. But for this, I think we want fairly clean carrier to set the standing waves up. I did sort of think about driving it. My first thought was, well, maybe it wants a fairly clean sine wave, because if you've got harmonic content it might be difficult to get standing waves. But then I thought, well, yeah, this thing's rattling up a piece of metal up at 28 Hz. It's going to be very sharply resonant. Pretty much any piezo device I've ever come across has got some very sharp resonance, which means it's going to pretty much only be resonating at that frequency, and there's probably not a great deal in terms of harmonics. So I sort of decided to use basically the simplest drive method that I could think of. These piezos are basically a capacitive load, but the impedance drops quite a lot at resonance, and they need a fairly high voltage. I mean, they're typically sort of 200-400 volt drive. So I basically come out with the simplest drive circuit I could think of. This is the transformer out of a small old ATX PC power supply connected backwards, so this is the original primary, and I'm just driving it with a N-channel MOSFET and a 555 timer. So I'm just literally sticking a square wave into the gate and just switching one of the formerly secondary coils, the actual one that was used for 12 volts, with the common connectors up to positive. I'll put a schematic of this on my website, but it's extremely simple. I originally did some tests with a function generator, but in fact I've used a multi-term pot so you can get some quite fine frequency tuning. This is set to tune. This will go from about 20 to 30 kilohertz over the whole range of the 10 turn, but you've got quite a nice smooth control over it. In terms of tuning, I found the easiest thing to do is just simply tune it for maximum power consumption. So outside of resonance the power draw is pretty low, but as you get towards resonance the power consumption increases sort of very dramatically. There's sometimes more than one resonance point, but the main resonance, you see it's going from about 100 milliamps up to about sort of 3 amps at resonance. And you also start getting all sorts of weird squeaky noises. Pretty much any loose bit of metal in the vicinity will start vibrating and making weird noises. Also noticed that it does occasionally seem to hop between different modes, and I think it also drifts a little bit with temperature, but also almost anything touching the surface of it will alter its resonant frequency. If there's, like, even if it's damp or even if it's got a small object on there, you do need to retune it to get the maximum power transfer. A couple of minor details: because we've got this outer and inner electrode, you want to ground this electrode, because otherwise the whole thing's going to be bouncing up and down at 300 volts, which if nothing else will hurt a little bit when you touch it, but also it will kick out a lot of noise which could cause the oscillator to go unstable. The other thing is, I just found that when I was adjusting this, the frequency was going a bit unstable when I was touching it, so I just grounded the shaft of the pot to stop that, just to get it a bit more stable. So the basic idea is we get sort of vaguely flat, sort of planar sound waves coming off the front of the transducer. Again, on some of the YouTube videos, they're using sort of concave transducers. Some of them had two transducers, some use concave reflectors. But all I've got is just a flat, the flat plane of the transducer. This is just stuck down to the base with blue tack, and just a flat plate. These are just 2 bits of 3mm aluminium with some M3 studding, so I can just use these. I can just use these spacers to sort of adjust it up and down, and then clamp it at the right position. So I've got quite fine control of the position. So obviously we need to set this up to be a whole number of wavelengths to get the effect. One thing you do notice is when you've got things like these screw threads, they'll start just turning of their own accord when the transducer's running, because the vibration just makes them vibrate all over the place. Right, a few of the demos I saw, we were sort of using things like water droplets, but also quite a lot we're using small polystyrene balls. The key seems to be a very low density, and the uniform shape of a ball helps. So you can sort of tune. The main thing to do is to tune the distance of this plate to get the standing wave set up. Although you can do it with individual balls, they just go all over the place. So I just made this simple sort of abacus probe. It's just a few balls. I melted a hole through the middle with a fine wire and soldering iron, just so they'll stay in one place. And if you just sort of wave this in the around the middle, and then just very slowly move the plate around, you'll suddenly see that they'll start moving or get wiggling around of their own accord once the plate's at a certain distance. Just crank the power on a bit. So there, so when I move that, you see they suddenly jump up. If I hold that in place as I move down, you can actually see them jumping at specific positions corresponding to the standing waves. So if we just get a nice strong pattern and just lock the plate off at that position. Still going. So we can see quite a lot of, so they're sort of jumping there. There's quite a strong attraction there. So if we just lock the plate off at that position. One problem with these polystyrene balls is they are obviously extremely static. I found if you put them in a little anti-static box and sort of shake them around a bit, that seems to be quite good at discharging them. The other thing is, whatever you use to put them in this area, you don't want it, even a pair of tweezers can actually affect the airflow. So I've came up with just this simple, which is a piece of wire with a loop on the end that you can sort of use as a little spoon to pick them up. Just put them in the stream. You will of course end up with these polystyrene balls everywhere because they just drop and they just go all over the place. Also, you also need to be careful not to have too many air currents because they'll just blow away at the slightest amount of airflow. It was actually surprisingly easy to get this working. It does take a little bit of tuning to get the maximum amount of lift. So once you sort of got something, it's then worth just spending a bit of time just very carefully adjusting the position of the plate. So it's not quite got enough lift there. Just right, I think the plate wants to be sort of fairly close to parallel, although you do sometimes get sort of streams going in all sorts of directions. There we go. The larger ones above a certain size, it doesn't seem to work that well because I think it's due to just the wavelength. The smaller ones work a lot better. So you've got a nice string of them. They do tend to form interesting shaped strings that, as you adjust sort of the frequency and power and plate position, the sort of string positions tend to change a bit. Some sticky. So if I sort of tweak that plate position, sort of moves around a little bit, it doesn't take much to sort of flip it off tune and they will just collapse. The other thing you do, I found, is that if you get a load of them clustering in this centre hole, that can also affect the tuning. Just having a few little beads in that hole, I think it must affect the way the sound comes out of it. And every so often you just do get a fairly random collapse. That might just be because I'm talking and it's getting blast of air, perhaps. One thing to bear in mind when you're doing this is the transducer will get quite hot, so just keep an eye that it doesn't get ridiculously hot. I don't know at what temperature these things die, but we're putting, this is running about 12 volts at 2 amps, so we're putting about 25 watts into it. Obviously not all that's going to be coming out, so we're running at less than half its nominal rating. And in fact, if you get the tuning dead right, you can actually get well below 10 watts and still get a fairly decent amount of levitation happening. I've tried using a few other things like powders and so on and smoke, and they just don't work at all. I think, if you think about something that you might think of as a fairly light powder like flour, the actual density is still quite high, it's just in small pieces, whereas obviously with polystyrene you've got a very high surface area to weight ratio. So I've actually yet to find, I've tried normal water droplets, just come out too big to do anything with, but say polystyrene, you can get a fair old amount of levitation going very easily. And there's probably also quite a lot of scope for playing around with different shaped electrodes. One thing I found, this plug, it's an M10 thread, but it's a fine pitch, so it's not the same pitch as a standard M10 bolt. But I have actually found that's actually an M8 stainless cable gland. And I found, although that thread is M8, the cap that goes onto it is actually fine pitch M10, which is the same thread. So I'm just experimenting with gluing that onto various different shaped things to see if I can get any improvement by just changing the shapes. Again, I don't really know what the resonant mode of this thing is, whether it's mostly pushing up in the centre or whether it's, it seems to be quite a lot, fairly well distributed across the front, just by judging by where things are tending to hover. But there is also a concentration in the centre. They tend to want to either come from the centre and sort of go out, or sort of, you don't ever seem to get any sort of hanging around the sides with the simple flat plate arrangement. As you adjust the frequency slightly, I don't think that the range of frequency adjustment while you're still in resonance isn't enough to really seriously affect the wavelength. So it's really more affecting just the amount of power that's going into it. So you adjust the frequency range is small enough that that's not really significant in terms of the plate distance. And it's quite surprising how much distance you can get. This is about 120 mil between the transducer and the plate. It's running about 50 watts going in, although quite a lot of that's coming out as heat, and that power supply does get quite warm. So Still a surprising amount of lift even at that distance. Doesn't seem to, I think the waves are concentrating towards the top, we're not really getting much at the bottom, but the waves seem to be quite nice near the top. It does start getting unstable when you have lots of beads, because obviously each bead disrupts the wave patterns slightly. So if you never get a complete string of beads. Also, you notice even very small amounts of air currents can also affect it. But the more beads you get in there, the less stable it is. Just trying to tweak the frequency. One thing that's quite noticeable when you're running at high powers is that the resonant frequency does drift as it warms up. So that's starting to drift. I'll get that back, so it's back up to about 4 amps. Yeah, we've got quite a nice pull there now. That's and obviously the other thing is just try not to run it at high powers for very too long, because everything just gets very hot. But yeah, this and the peak, just looking at the current, this is actually drifting literally over a few tens of seconds. It's changing by about like sort of 200 milliamps or so. So this is clearly getting quite hot. But so you can get a fairly impressive string of beads going. It looks like the resonant frequency is dropping as the temperature is increasing. So I'm having to turn the frequency down to keep the current up to the maximum. We're getting a fair old number in there. So we got in there, yeah. See if I can get this full string before it starts smoking. It's actually surprisingly stable for that number of beads. Also, as you adjust the power, you do get all sorts of weird, like for example, you get sun instability. So when you're doing this many beads, you really need to pretty much have your hand on the adjustment pot and just fine tweak it and hopefully catch any instabilities before it all collapses. It's a bit like sort of ultrasonic Jenga. I think actually some of the beads that have fallen into this hole might have actually stabilised it a little bit by damping the sort of turbulence near the bottom. Nearly got a complete string there. This is actually the longest I've ever had. Yeah, it's very hard to get them, especially at this long distance. It seems to be quite hard to get any stability near the bottom. The transducer, there's probably quite a lot of turbulence floating around. And also I suspect if I just move a flat reflector even near it, it's probably going to have some effect, because we're getting waves sort of bouncing off. Yeah, you see you're actually pushing and distorting it. Obviously there might also be some electrostatic effects as well, because obviously the polystyrene is very staticky. Oh, I think my power's dropping now because the temperature's going up, so we're losing a few, but that's a pretty impressive stack. Right, one of the YouTube demos actually was quite neat. It showed visualising the standing waves using dry ice. Now I'm not having any dry ice, but I do have a CO2 fire extinguisher, which if you fire it into a bag will actually give you a few little flakes of dry ice. You can actually see the layers of the standing waves. I haven't yet found anything else that works as well as this, which is a bit annoying. Something else that you can use for tuning is you get a little bit of tissue paper. You can see it. sort of gradually finding some places it likes to sit. So I think one of the problems with anything other than the balls is the shape's fairly irregular. I don't know, you can get some tissue paper to sit. That's all right. I haven't yet managed to get any liquid droplets to float. I tried water, but I think the surface tension makes the blob too big. I've sort of tried some alcohol, and again, even there, you can actually see, just about see a sort of slight pulling effect on the blob, but it doesn't really do anything. I have occasionally managed to get some nice little clouds of alcohol vapour. Probably a little bit difficult to see. I think it's sort of the combination of when it drops onto the transducer, which is quite warm, it seems to evaporate, and obviously the ultrasonic effect also vaporises it. And I have actually managed to get some little spinning clouds of sort of alcohol mist. So maybe it's quite hard to get it to go any further up than just off the surface. But when those sort of clouds do go to the sort of the standing waves, you do actually see some sort of layers like you do with the dry ice. Let's try a bit more. Obviously bear in mind that atomising alcohol like this is a somewhat flammable atmosphere, so you need to be a little bit careful. One thing I was a little bit surprised at, it didn't really seem to have any effect at all on the flame. Well, I wonder if that's because the gas density within the flame is different, so perhaps it breaks up the standing wave pattern, but you get a little bit of sort of deflection, but it doesn't really seem to actually do anything. This is some very thin aluminium foil. It's called a wrapping foil. It's just the cheapest, thinnest foil you can get, and you can actually see quite clearly the standing waves there. Interesting thing about this thin foil, I think, because it's effectively metal, the ultrasonic waves do actually pass through it, so although it's fairly heavy, you can actually, it feels like it's almost wanting to lift it. I think it's more the aerodynamic instability than the actual size. So I get a fairly big piece. It's feeling like it's wanting to float, and it sort of tends to sort of float off to the side rather than dropping down, which suggests that maybe, I mean, that looks like to me like there's possibly enough lift there, but it's just not stable enough aerodynamically to quite float. So bring the power up a bit. Yeah, and if you hold it, it will actually support itself, but I think you need to find the right shape to get it to actually levitate and hold in position. I have got some really a small little sliver of that foil to levitate. It's interesting, it's sort of spinning quite fast. I think that's probably just the aerodynamic instability is biasing it, so it's deciding it's going to go around in circles. Try another piece. Yeah, so add to the list of things we can levitate, very small pieces of very thin foil. Right, so I was thinking what else is really sort of light, and I thought, oh, bubbles. So started having a little play with soap films, and you can actually visualise, get the angle right, you can actually see the standing wave pattern disrupting the surface of the film really clearly and easily. Yeah, this works pretty well actually, for sort of just, you can just wave the thing through the field, tweak the frequency, and actually see all the standing wave patterns pretty much instantly, which is a rather nice way of setting up. Nice pretty colour patterns as well. You've got to watch if you drop any liquid onto the transducer, that knocks it out of tune and damps it a little bit as well. That is pretty awesome. Let's see if I can get some bubbles trapped. It's very hard to just get a loose bubble. You can see they're being affected by the you can actually see the bubble changing almost from clear to it goes sort of translucent because of the waves vibrating the surface. It's getting a bit of a pain using tweezers, just figuring out how we can dispense these balls automatically. I thought just sort of stick them in a tube and sort of poke them out one at a time. I tried a plastic tube, but it's way too staticky, it just clung. But this, I just made a tube by wrapping some of that thin foil around a screwdriver and sellotaping it. You can actually dispense, and just sort of poking it in with a file. You can actually dispense them quite nicely. Right, this is a fun little gadget, probably quite a nice thing for sort of science fair type things. One thing I think I might try is actually getting a second transducer and have them facing each other to get more powerful levitation. One issue there might be how well matched the resonant frequencies are of the two transducers. So you probably have to set a frequency which is like midway between the two peaks. But what you may also be able to do is by adjusting the phasing of the two, you might actually be able to control the vertical position by adding a phase offset at the same frequency. So I think I'll probably have a go at that. But it would be nice to be able to get some sort of liquid droplet levitation, but I suspect that could require quite substantially more power. Also, it's something I might try and sort of figure out a way of getting shaped surfaces on here to try and concentrate it. But the other thing is the driver isn't particularly efficient right now. Like how high power this thing gets red hot. I think the transformer's probably saturating, so I'm just driving it single-ended. So probably some sort of push-pull driver may well be more efficient. Plus, obviously, I can use a bigger transformer to get a bit more power into the thing. But yeah, it's quite a fun little thing.